We are now recording, and this basically summarized what we should have gotten out of yesterday's activity. So, when we looked at function after function after function, I asked you to look at certain things. One was, what are the ends of the graph doing? Are they doing the same thing? Are they doing opposites? What are the ends doing? What do you think made the ends do those things? We'll all dance together in just a minute, because I see you laughing at me now. Okay? And what is happening at the roots? So those were the two things you were supposed to be looking out for yesterday as you did the task. So the big picture ideas that we talked about were the degree of the function and the sign of the leading coefficient determine what the ends of that graph are doing. If the graph has an even degree, the ends are doing the same thing. They're either both going up or they're both going down. Okay? If, and that was here, if that even degree has a positive leading coefficient, those ends are both going up. If that even degree has a negative leading coefficient, those ends are going down. Okay? Now the other one was an odd degree. If a function has an odd degree, the ends are doing the opposites. Okay? If it is an odd degree with a positive leading coefficient, it falls to the left and it rises to the right. Kind of looks like y equals x. Falls to the left, rises to the right. If it is odd but has a negative leading coefficient, it's a reflection of that. So it rises to the left and it falls to the right, just like y equals negative x. Okay? So that was one thing we looked for. What are the ends doing? The other thing has to do with the factors. The factors give us what the x-intercepts are, and it also tells us what's happening at those roots. Is it passing through? Is it bouncing back? Okay, so if a factor is raised to an even power, then at that root, the graph is tangent. It touches that x-intercept and bounces back. If a factor is raised to an odd power, it's going to pass through. But there's two ways it can pass through. It's going to either pass through like a straight line, if that odd power is 1. If that odd power is greater than 1, it passes through with an inflection. It causes a change in concavity of the graph at that point. We'll look at that in just a second. This one, how do we find the y-intercept? If it's in standard form, it's really easy. It's the constant. If it's not in standard form, if it's in that factored form, which many of them were, you would have to plug in 0 for all the x values and multiply out the constants that were left. Now, how do we find the x-intercepts? Those are those x values of each factor that make it equal 0. So what can I plug in for each x value for each individual factor that make the factor equal 0? And that was our big idea from yesterday. So how did we use that on our homework? Well, let's look at it. So, number 1, DCBA. How do we know number 1 is D? We look at the degree. 1 plus 2 plus 1 more is 4. We know the ends are doing the same thing. Now we actually know the ends are rise, rise. Because not only is it even, but it is positive. So that tells me it could be B or D. And then I look at the roots, or my x-intercepts. I have an x-intercept at 0. It should pass through there. An x-intercept of 3. What does that 2 tell me it's going to do? Bounce. And then an x-intercept of -4. What's it going to do there? Pass through. So when I come look at Z, it's rise, rise. It passes through at -4. It passes through at 0. And you see it bouncing at the 3. Okay. Let's look at 2. 2 is C. I know it has an odd degree. The degree is 5. X squared times x squared. 5. 2 plus 1 plus 2. 5. And it has a negative leading coefficient. So, odd tells me opposites, but the negative leading coefficient tells me it's going to rise to the left and fall to the right. Okay? So the only one that does that is C. So we don't actually even have to look at our root behavior, but did it bounce at 0? Yes. Did it bounce at -4? Yes. Did it pass through at 3? Yes. Okay, number 3. This one has a degree of 4 and a positive leading coefficient, and it's going to pass at 0, pass at -3, and bounce at -4. You see the little bounce right there. Bounce, and then pass, and then pass. So that one's B, and that leaves A for number 4. It's even and negative, so both ends will fall. Fall, fall. Really all we had to look at, because it was the only one that did that with the end behavior. But let's look at the individual intercepts. This is squared, squared, squared. So it should bounce, bounce, bounce. Got it? All right, let's look at the next section. All right, I'm going to graph the first one with you. This one, how do we graph? Step 1, plot the intercepts, the x-intercepts. Okay? So my x-intercepts are 0 and positive 1, 2, 3, 4, 5. Very good. Because that's what makes each of those factors equal to 0. Now, this has a degree of 3 plus 2, so the degree is 5. And if I were to multiply it back, my leading coefficient would be negative, which tells me it's going to rise and fall. Now, this one, at the 0, it's raised to the 3rd power. Okay, that actually means it has multiplicity at that root. And that odd multiplicity causes an inflection. So it doesn't just pass through, it passes through where the concavity of the graph changes. If you look at the left side, it's concave up. If you look at the right side, it is concave down. So if a factor is raised to an odd power greater than 1, that means it has odd multiplicity of that root. It passes through, but it passes through with an inflection. If it's just to the 1st power, it passes straight through, no inflection. But if it's an odd power greater than 1, it's got to change concavity there. Concave up to concave down. Now if I were approaching it from the bottom coming up, it would go concave down to concave up. Okay, so the concavity will change. Now, this factor is raised to an even power. It also has multiplicity at the root. There are multiple, more than 1. Isn't that what multiple means? So it's multiplicity because it's greater than 1. And it's even. When it has even multiplicity, it bounces. It is tangent. Okay? So, let's look at this one. 4 and 2 is 6. Positive leading coefficient. I would plot -3. I would plot +1. Even, positive. Rise, rise. This is how we do it. Step by step. Plot the intercepts, do the end behavior. Last thing to deal with is the root behavior. Okay, at -3, it's even. The factor is raised to an even power. Bounce. At +1, it is also even. Bounce. Now, Do I know where that point is? I have no idea. I do not know how high this goes up. That is not what I'm looking for right now. You can learn that in a later class. But right now, the only way we're going to figure out what that local max is right there is to use our calculator. We're not doing that by hand right now. Okay, now this one. This was not in factored form. So to graph it, first thing we have to do is factor. And when we factor, do you see I have 2 of the x plus 2 factors? So I should write this as x plus 2 squared. I have 2 of the x minus 2 factors. So I should write it as x minus 2 squared. And so it's going to bounce and bounce. Questions? Okay, so if we're trying to write a polynomial whose graph has the following characteristics. Okay, it's rising and rising. So that means it's an even degree function with a positive leading coefficient. Because it's going to positive infinity and positive infinity. So the ends look like this. Even and positive leading coefficient. The graph is tangent at both the x-intercepts. So tangent would be second power, second power. That's an even degree positive leading coefficient. Yes, sir?
So if you factor in an equation that had a GCF that wasn't x, how would it change the graph? Say you had a GCF like 2.
Okay, what a 2 does is it causes the vertical stretch. It does not change end behavior. It does not change root behavior. It changes where those local max and mins are.
Okay, and then I assume that if it were a fraction, it'd be like 4.
And all that would vertical compression. Yep. All right. So if I put a 2 in right here, it's going to change that y-intercept. Okay, but I'm going to take it back out because I didn't have to have it. Now, for my graph, what is my y-intercept? Plug in 0 for x, squared, and squared, multiplied 100. It is the point 0, 100. Now, if you put a coefficient in front, you're going to have to take whatever your coefficient is and multiply it times 100. Yes, sir. Okay. So some of you were probably shooting in the dark last night on some of this. Does it make sense now? Cool. Awesome. All right. So here is a nice little summary. It's like picture perfect if you wanted to take a photo of it.
I wish I drew what you drew yesterday, and it helped me.
Good.
It didn't help me on the back, but it helped me on that. I'll take a mental screenshot.
Wait, what were you talking about fighting the men's and max?
Because I can't get the pictures on my phone. I'll save the audio.
Did y'all not do that last year?
We didn't do graph on that.
Y'all didn't use graphing calculators at all?
That's a
Okay.
pain.
We do that Monday.
Okay.
Okay, right while you guys are taking a photo, screensaver, that's awesome. I will not be here Monday, but I have found a recording of me teaching Monday's lesson to another group of students
That's dedication.
3 years ago. So, you're going to hear me talking to these students. You're going to hear me talking about an upcoming test or quiz. Your quiz is Wednesday. On that recording, it probably wasn't Wednesday. It was probably a different day. We probably started school at a different time of the year. We used to teach this at a different time of the year. So, your quiz is still Wednesday. Ignore that. But the material that I talk about is the right material. So, bring your calculators Monday. You're going to need them. You can follow along on the video. I'm actually going to post the video this weekend. So if you'd rather watch it, you can link from Willoughby World, or you can link from Blackboard. Watch the video this weekend, and then you can use Monday as a work day. Okay? And I'm going to tell the staff that I have given you this assignment ahead of time. If you chose to do it ahead of time, then you will just be working during class and not watching the video. If you want to watch the video Monday during class, it'll be playing Monday during class. But keep in mind, it's me teaching other students. So, You'll see not much has changed. I'll probably make fun of somebody. Probably encourage somebody else. Yes.
Do you know what our sub's gonna do?
I think our sub is Miss Hatch.
I do not like this Stacy.
I haven't seen him in a while.
Usually it's not bad.
Okay.
This is like,
I love this.
yeah.
Alright, so this is everything we just talked about, right? Okay, so let's look at number 1 on the worksheet you guys picked up as you came in. Now, number 1 is awesome, but it was tricky. So, we're going to do number 1 together because I was a little bit devious for making this one the first problem. Alright, so what do we need to do when we graph? We need to do a couple things. Okay, good. Let's find the x-intercepts. Alright,
Negative 3, negative 3, 2.
negative 3 over 2.
Positive, my bad.
Okay, when we move this over, it does become positive. So it's positive 3 over 2. Positive 3 halves is 1.5. So I'm going to plot one of my x-intercepts at 1.5 because of the first factor. All right, let's look at the second factor. What x value will make that second factor equal 0? 4. Good. Okay, 4 makes that, if I plug in 4 for x, it makes that factor equal 0. Okay?
Yeah.
Last factor. What x value makes that last factor equal 0? Negative what?
You've missed all 3. It's alright, Joanne. Those things.
Alright, so that's the first thing we need to do. So 1, we'll find those x-intercepts. The roots of our equations. Alright, now 2, we're going to determine the end behavior and we're going to graph it. So to determine the end behavior, we need to know 2 things. The degree of the function, and is the leading coefficient positive or negative. So if we look at the degree, when you're multiplying here, you add the exponent. So it's the understood 1, the understood 1, the understood 1, the degree is 3. Now this is tricky because it looks positive, but it's not. Because if we were to multiply this back, the leading coefficient would be the one where we multiply all our x's. It's that third degree. Well, what is a positive x times a negative x times a positive x?
Negative.
It's negative. So this leading coefficient is sneakily negative.
So it's.
That's why we're doing number 1 together. So, odd and negative rise to the left and fall to the right. Okay. Next thing we need to do is individually look at the root behavior. Is it tangent at the root or does it pass? If it passes, does it pass with an inflection or just straight through? Okay? First power, first power, first power. Straight through. So we go straight through, straight through, straight through.
What a beauty.
Okay. Hopefully yours looks better than mine. Now, is this point, are these 2 points located in the right spot? Probably not. But I'm not grading that. What I'm looking for is a sketch that has accurate x-intercepts, accurate end behavior, and accurate root behavior. Cool. I like this too. All right, let's skip to number 7. Yes.
Did we ever escape geometry?
We've pretty much escaped geometry.
This doesn't feel like we've escaped.
These are functions. I'm graphing polynomial functions. But geometry's not graphing. It's figures.
No, I still see shapes though.
See shapes and everything.
What shape is this?
That's so pretty.
So it's odd and
All right. So First, we identify intercepts. What makes this factor equal 0? 1. There's an intercept. What makes this factor equal 0?
-2.
-2. Okay, so those are my x-intercepts, and that's how I find them. All right, and the behavior. That's the next thing. So I have to look at the degree, which is 5, and the leading coefficient is, okay, so it's odd and positive. Fall to the left, rise to the right. Okay. -2. This factor has a power of 2. So it's even, it will bounce. This factor has a power of 3, which means there's, right. Okay, so this is odd multiplicity. Going this direction, it goes from concave down to concave up. All right, even multiplicity, bounce. Odd multiplicity, passes through with an inflection.
So it's a 3.
Got it? Okay, so now let's go the other way. I give you the graph, you give me the equation. Yeah. Okay, now, I have 2 examples here. We're going to do these, give a possible polynomial function of least degree. I added that because if it bounces, it's just a sketch and it's bouncing, it's tangent. It could really be any even factor. But I'm going to say of least degree, so we just choose 2 if it bounces. Okay? Now, with odd multiplicity, because I said of least degree, don't choose 5 or 7 or 9. Choose 3 if there's an inflection.
There's an inflection.
I see the inflection.
Okay, so we've got an x-intercept, an x-intercept, an x-intercept. So this is at -4, so it would make x plus 4. This is at 0, x minus 0. You don't normally write x minus 0.
Teacher, sorry for the interruption, but students, if you participated in the Feed Your Need to Read drawing, it is now time to announce the winning numbers, so please pull out your ticket. The numbers are 51079005 and 510813.
Okay. Okay, it's bouncing here. It's passing here with an inflection. And it's passing straight through. 2 plus 3 plus 1 is 6. Oh, good. It's rise, rise. So this works. Now, if we were to actually write this, generally, we start with the monomial. We wouldn't write x minus 0. You'd write x cubed. And then we might do the x minus 4, because it's a binomial. And then the x plus 4 squared. Now, really, the only thing that has to happen, we start with monomials. The rest of the factors really could be in any order you want. But we always start with monomials. Okay? Now, we know this one is odd degree, negative leading coefficient. Because it's opposite ends, and it rises to the left and falls to the right. We're going to have an x plus 2 passing straight through, an x minus 2 bouncing, but we know it needs to be negative. There's my equation. Okay, so your homework is to finish up that worksheet.
Oh, in the back?
Okay? My video Monday will go over the homework, and it'll teach you the next lesson. You're welcome to watch it this weekend and use Monday as a work day. Bring those graphing calculators.
Is the back number 2?
Yeah, front and back. It doesn't take more than like 10 minutes.
Wait, what?